Yeah, so great, being recorded, perfect. Yeah, so I reached out to Kevin a month or two ago, offering to do a talk on clustering because clustering is kind of a fundamental, nice problem to study in machine learning and statistics, and kind of a lot of like data modeling, analyzing data, finding like a natural question in analyzing data is like, what sort of groups do we think maybe there are in our data? Because that can help us maybe reduce dimensionality in our data, maybe try to, uh, instead of trying to capture all relationships across the entire data set, maybe we can kind of break down the data set into subgroups, which maybe can be modeled more simply when separate. There are a lot of reasons to maybe want to learn a structure in data when we're presented with it. But a fundamental problem is like this is a problem of learning something we don't have labels for. So it's like an unsupervised problem. So like, who here like maybe like raise your eyebrows if like you're familiar with like terms like supervised and unsupervised. Okay, cool. Yeah, I've seen some eyebrows. Cool. Yeah, so who here is like familiar with k-means clustering and Gaussian mixtures? Maybe something that's like more clear is like if you raise your hand. Okay, cool. So like most people. So what I think the best way to kind of approach this, I have a few things to kind of share here. And I was kind of talking about this with Kevin beforehand. What I may do is kind of start with the kind of coolest, fastest, kind of nicest way to learn clusters and data, which is called Gaussian mixture modeling. There are, so actually what I'm just going to do is, to keep this meeting engaging and fun, I'm just going to like start a visual demo. So like what I've done here is a few months ago, I was doing an independent project where I implemented some of these algorithms from scratch to kind of learn what's actually going on under the hood. So what I've actually done here is I defined a Gaussian mixture myself, where like I know what the mixture components are. I generated a bunch of data from it. And then what I wanted to see was, based on an implementation that I made of Gaussian mixture model learning, can I reproduce or like recover the original kind of generating distribution? And what a Gaussian mixture is if for those who like aren't familiar already, is it's just a combination of Gaussian distributions. So a simple Gaussian distribution would be like one bell-shaped curve, but maybe the down here, actually, the data that I sampled here, this is the original distribution. It has like one component here, a small one here, a small one here, and like a larger one here, maybe another one here. So all it is just a few Gaussian distributions, each of which has a mean and a standard deviation, and each of which has a weight that corresponds to how much does it contribute to the overall mixture. So in learning a Gaussian mixture, if you kind of imposing the problem, the parameters, so to speak, to learn are those three things across the whole mixture.
4 West and County Road 535.
Oh, someone has some directions. Cool. So those are the things to learn, and I'm going to go over a few different ways to learn that. And so here I'm going to show a visualization and explain how this actually works. We go up here. So this is an algorithm called expectation-maximization, where we start with an initial guess for what we think the mixture components are in terms of their weights, their centroids, or the means, and their standard deviations. And then this algorithm is iteratively updating those values to improve the fit. And you might ask, how is the fit quantified? Which is a good question. It's simply one way to define that is the log likelihood of our data based on the mixture that we're considering. So this is kind of like what it looks like, it takes, I don't know how many iterations this was. About 400, took about 400 iterations to kind of basically recover, just about recover the original distribution. So what I'm plotting here is previously there was only the kind of original generating distribution, but then I'm also plotting, the green line is what the kind of mixture is that I'm learning, and the individual points are the individual mixtures that I'm like updating as part of that algorithm. And the way that this works, I don't want to like, I'm going to like go into my code in a moment, but I don't want to just like jump to a bunch of code because that's going to confuse people. But the way that this works is starting from data. If we start from a few candidate, where like we have an initialization step where say we think that there are 5 mixtures, we'll like randomly guess the locations of 5 mixtures. And then based on those 5 mixtures, we can, for each one of our data points in our sample data or in our training data, we can compute probabilities of how likely, say like, for each observation or data, what is the probability that it came from mixture component 1, mixture component 2, mixture component 3. So we can do all these kind of probabilistic assignments for each one of our observations. How likely do we think it came from each of the candidate distributions? That's the first step. And then a second step is, based on all those probabilistic assignments, update what we think the mixtures are. And then so we would update what the means are of what we think that, like for each one of the mixtures, look at what the probabilistic assignments were from our training data, and then update the means of each of those components based on like what is the weighted average of each of the training data, weighted by the probability that we thought it was due to this component. I'm going to pause in a moment. But that is overall how this algorithm works. It first does a probabilistic assignment, and then based on those assignments, it updates where what we think those parameters are. And then based on the parameters, does another cycle of probabilistic assignments. So it's like assigning the data based on the guess of the parameters, and then updating the guess of the parameters based on the assignments, and then kind of just going in a loop until convergence is reached, and it doesn't improve anymore. So maybe I'll just kind of like pause there a moment. That is kind of like Gaussian mixture modeling in a nutshell. And I'm going to go into more, but does anyone have any questions with that so far? Like, does this make sense? Hi, Robbie.
Hi, thank you. So this talk appears to be more about manipulating data to meet expectations as opposed to realizing the reality of any given situation based upon the data. Is that a fair assessment?
Could you say that again? I'm sorry, I just want to make sure I understand that.
So it seems like—
Is this in the comments?
No, but here, based upon the here, paste it in. Sorry if my rough notes is that's a very first draft.
It sounded like you're perhaps reading from something that was written.
I had written it because I was coming up with the idea, and then you asked for questions.
That makes sense.
Is this a correct assessment of the technique that you are deploying?
Let's see. I would say this is not. I would say this is more about the latter, actually. So to just kind of reiterate, if I may, what you're asking, if this is kind of more about, on the one hand, manipulating data to meet expectations. So would that be like data cleaning, for example, maybe, or like denoising data, like manipulating data to meet expectations? Would that be an example of the former? If I understand you correctly.
I'm going to remain silent on that.
Pardon?
I'm going to remain silent on that. And
okay, that's okay.
Like him.
Fair enough. So all this is doing, it's not, to be direct, it's not manipulating data. The only thing, all we're doing here is we're trying to make educated guesses about structure that we haven't actually observed. So, and when I say like structure, I mean, we think that our data can be summarized by a few Gaussians together. So as an extreme example, let's say our data looked like it just kind of had one big blob. Maybe we would just want to learn a single Gaussian from data. We would try to be like, you know what, what is the mean and the standard deviation of our data? That would just be the most simple Gaussian mixture. It would be a mixture of just one single Gaussian. But the fundamental problem there is we're supposing that our data came from some generating distribution that we don't know what it is. And we're just trying to make a guess of what maybe some structure out there in the world is that led to us having the data that we have. So that's, it's another word for this is like latent variable modeling. So what latent variable or latent models are about, positing the existence of variables that we don't observe, but we want to try to infer what their value would be based on other data that we can see. And that's what's happening here. Where the only thing that we know is just the data that we're given. So this histogram. And from that histogram, we're trying to learn a few Gaussians that, when added together, to be very precise, have the highest probability of resulting in the data that we see. So, wait, did he go away? Where did he go? Or did things just reorder on my screen? I'm not able to see everyone under one. Oh, here we go. Now I can see everybody. Okay, people are asking us. Let me see some other questions here. Does the underlying assumption to start the modeling is that given data is a mixture of Gaussian, the assumption valid for all kind of real world data? Yeah, okay, good question. So one basic thing here is in my example, I am only working with data that exists along a kind of a negative infinity to infinity continuum, like real numbers. If we were dealing with categorical variables, we would not be able to use this approach. We would want to do maybe mixtures of categorical distributions, like a Bernoulli for binary data, or Dirichlet's if categoricals if we were working with more than one group. But for this situation, if we're dealing with data that's just like continuous real numbers, then we can use this approach. So for example, the Iris data set, which actually would have been a good example to work with. The Iris data set has a bunch of measurements of like sepal lengths and petal lengths and widths. These are like continuous values. We could like use this method on data like that. So anything that is just like a floating point arbitrary number. And okay, great, cool. So now kind of like with, I think at this point, it makes sense for me to maybe go into the implementation of how I made this. So there's like a few, let's see, do I want to go into implementation or, yeah, I'll just discuss a little bit how I made this. So this plotting here, this is Plotly. So overall, how I've kind of structured things is in this Jupyter notebook, I have a Plotly figure that I am updating the data in. And then I made a Python package where I've implemented my source code for, I defined like a class for a Gaussian mixture, and then also a method for implementing this algorithm for updating the Gaussian mixture. And what that looks like is I have like a univariate Gaussian mixture class where like it's just parameterized by weights, which are for each individual component, how much does it contribute to the overall mixture? They have locations, which are the centers of each Gaussian, and then scales, which are the standard deviations of each Gaussian. And then naming convention here, I used lokes and scales because if you've ever used NumPy or most other, at least in my experience, the things that I've used, things like the mean and the standard deviation or the variance for normal for a Gaussian distribution are called the lokes and scales. I implemented a sample method so I could very easily generate a bunch of data. I also implemented a probability density function, which given some data gives me a number of like what is the probability of seeing that data based on the current guess of the Gaussian mixture. This is important because this gives me a direct metric to evaluate like the goodness of fit of a candidate mixture based on some data. And then in here, this is difficult to probably walk through, but this is an implementation of the expectation maximization algorithm, which is what I described of doing probabilistic assignments followed by updates of the parameters and then kind of doing that in a loop. And where that kind of the magic for that happens is I'm doing this in just like a while loop. I update, I do an update. Oh yeah, this is really where things are happening. I do it like this is a single update step. Oh, Vulcan, does Vulcan have a question? Greek god, Vulcan. Or perhaps Greek god Vulcan just had his mic off, or mic on. So what this is doing in a single update step, we compute probabilities for each individual observation of it coming from each of the mixture components. That's the probability of Zi given Xi, where Xi is the individual observation, and then Zi is a latent variable that is the probability of coming from each of the other each of the components. I hope this all makes sense. And then based on these, this is the probabilistic assignment, and then we use that probabilistic assignment to compute new values for example, the weights, new values for the centers of each of the components, and then also scales for each of them. And the way that the weights are computed, I'm not going to go into the kind of background math of, you might be wondering, okay, like we are computing these probabilistic assignments, and then we're updating the parameters in this particular way. Like, why are we doing this? I am not going to go into the derivation of why, but if you're actually interested in, I would recommend, if you kind of want to go dig a little deeper into the machine learning of this, probably the best book to look at is, well, I'd have to bring this here, but there's like a whole chapter in this book all about Gaussian mixture models and the EM algorithm, and it kind of like has like these nice kind of few nice plots where this is going to be like too much to go into right now, but I would recommend, if you kind of want more like a more rigorous treatment of kind of like where some of this is coming from, this book, Pattern Recognition and Machine Learning, is fantastic, and it's also available for free, I think, online. So that's something to keep in mind. So that's kind of how this algorithm works. I'm also doing all this in NumPy. I'll maybe we'll just kind of pause there for a moment. Does anyone have any questions based on this? And also let me see the comments section. Oh yeah, can I drop the title? Definitely. Let's see. Mission and Machine Learning by Bishop. There we go. So happy reading. The beaches are a little chilly now, so time to stay home and just read some machine learning. So I think at this point, if there aren't other questions, I may talk about two other approaches to this problem, because the title of this talk also mentioned k-means. You might wonder what happened to k-means. So in this entire framework, it's using we're using probability theory to come up with like probabilistic assignments, and then based on probabilistic assignments, make these updates to the mixture components. And I think that this was kind of formulated for the first time in like the 70s or so. And actually, Yoshua Bengio, in one of his first papers in the 90s, published a paper analyzing the convergence of one of these algorithms. So Gaussian mixture learning is, well, it was probably before I was born, but even earlier in the 50s or 60s, a algorithm called k-means was invented, or an algorithm for learning k-means. So what k-means is it's very similar to Gaussian mixture modeling, but without any probability distributions. So instead of saying, oh, I think, if we look actually at this example that I made, let's say a data point happens here, right around -5.5. It's kind of between a few, it's not maybe clear which component we want to assign it to. It could maybe come from kind of the right-hand tail of this this lower one, or actually if we kind of look at some of these concrete actually sampled data, we might think, well, maybe it came from this this component to the left. Maybe it actually is from kind of the fatter left tail of this other component. The Gaussian mixture approach gives us a principled way of saying, well, I'm not going to give a definitive answer. I'm just going to compute probabilities for any potential answer. But k-means basically forces us to decide. Either it came from this component or it came from another component. It's basically a very highly contrastive version of this, where it does the same kind of iterative assignment and update procedure, but the assignments are for each data point in our sample here, as we would kind of go through the algorithm. Each one of these observations that in our data set would be assigned to one component with 100% certainty. And that simplifies the math a lot, and is much faster, but we suddenly don't really have any notion of, we don't have a probability distribution that we can kind of sample from anymore, because in k-means, there's no notion of like a standard deviation, or there's no parameterization of a probability distribution at all. It's just saying, I have k mixtures, they all have a center point, and I just think that some data came from this point, some data came from this other point, and it's using that same update procedure, and that was That's called Lloyd's algorithm, and it was invented sometime in the 60s. It probably, Lloyd's algorithm and what I've shown here with Gaussian mixtures are two sides of the same coin, or maybe two steps in an evolution. Basically, the Gaussian mixture is a probabilistic generalization of that k-means clustering. So I actually do have kind of a demo of, I want to hide this video panel. There we go. How am I on time, Kevin? I can probably go for another 5 or 10 minutes.
Did you ask how much time you have?
Yeah, I was just wondering how
Oh, you have. We've scheduled for 4:30.
Oh, okay. I probably have like 10 more minutes or 10, 15 minutes. Things I'll go over my source code too if people are interested. So let's see. Here I need to activate my virtual environment, I think. So in addition to what I'm going to go over now is previously I showed a Jupyter Notebook where I have this like plot that's kind of iteratively updating. I also have just some like examples. Let's see, just from the command line, and these compute a little quicker. It's a little easier to see. So this is like a very simple example. I'll just kind of let this finish. So what just happened here, and I'll run this again so we kind of get a look of kind of how things are progressing. This is the same algorithm where I started with a Gaussian mixture. And then I just want to see if I can, like, if I sample some data from it, can I recover the generating distribution again? So here, like, something weird actually looks like maybe happened here. It's a little unusual. Oh, no, everything's fine. So as you can see, this oracle, this is like, the original truth, had weights of 0.44 and 0.55. One was centered with a location. One was centered at negative 2.7 or so. One was centered at 1.8. Just raise your hand if does the concept here of like the weight, slopes, and scales make sense? Are people kind of following? Send a message in the chat, maybe.
Can you elaborate on it?
Yeah, sure. Okay, so what these, I'd be wondering, what are these values here, the weight, slopes, and the scales? So just a Gaussian mixture as a collection of Gaussians is just a weighted average of a few Gaussian, individual Gaussian distributions. So, so when I say like a weighted average, it's like, if you kind of look at this here, these kind of curves here, they originally, does it kind of make sense how these would be kind of a few, like 5 Gaussians summed together? Like there's one centered here, one centered, maybe I can actually rerun this with like 2, and I can do like 1,000. And maybe it'll be clearer. Let's see. Here we go. Oh, interesting. Very. So this red sign, I'm just like rerunning the example with a simpler, kind of simpler example. This orange line here is the it is a Gaussian mixture where all we have here are two Gaussians added together, and they're not centered. They have different centers, they have different standard deviations, but we're maybe just kind of like taking one fraction of one and then another fraction of another. Does that make sense?
I think so. So for the first, the original data set, the one that had 5 distribution would be 5 weights, not 2. It only had 2 weights.
You broke up a little bit. Could you say that one more time? The one with 5 had what? I'm sorry. I don't know if others are experiencing this, but it is a little, maybe it's because I'm doing some computation.
No. Yeah, Mina broke up. Mina, you can type your question in the
okay.
chat.
Would that be possible? By the way, I appreciate your asking questions, Mina. It takes a bold soul to ask questions. Yes, that's correct. So if we have, if
I'm having some trouble with my connection, so I just hope
no, we got it. That's okay. Zoom episode. It's all good. Yeah. So to clarify, if we have k mixtures, or say k components in the mixture, then we will have k weights. We will have because there's going to be one weight for each component, and where that weight it's called like a weight vector. So if we have like k components and then we're summing them all up and taking a weighted average of them, we would call that like a weight vector. It'll have length k, and it will sum to 1. So it's kind of like a the United States is like 0.45 Democratic, 0.45 Republican, and 0.10 independent candidates, or something like that, right? It's like a proportion. So it's just called a weight vector, or a probability vector, because it will sum to 1. So that's all that is. And then also, so like for each of these components, we need to learn what its weight is. We need to learn where is it centered, and then how wide is it. So that's just like the parameters of a Gaussian distribution. So if we go back to so you can kind of see here. So maybe just kind of clarify with the visualization that I made. I'm trying to visualize all these things in one plot, and it's rather ambitious, but the height of each of these is the weight for each of these kind of little dots. The error bars correspond to the standard deviation, and their like location on the x-axis is just the location. So I'm not going to run this again because it takes like 10 seconds for my Jupyter notebook to refresh and everything. But if I go back here, that's why I have like 2 values. In this example, I have a mixture of 2 components. And where I started off, I just randomly, I had like a random number generator decide a mixture for me. That's where this is coming from. And where they have these weights, these locations, and these scales or standard deviations. And so as you can see, kind of at the end here, it actually was able to like learn almost exactly what the original mixture was. It has them swapped, but that doesn't really matter whether something is mixture component 1 or mixture component 2. It doesn't really matter. So here we have like it learned like 0.556, it learned 0.4439 or 0.44369, roughly to a thousandth of a probability. It also was able to recover the scales and also the locations. So that's like pretty good. So if we can kind of compare, actually, I'll just run this again. So if you kind of are able to look out for how the oracle and the learned is going to be changing, and then we'll be able to kind of see how fast it changes. If we do this again, so you can kind of see it converges pretty quickly. So that's pretty nice. You might say, well, this is an easy example, William. You only have 2 mixture components. They are pretty far from each other. What I could do here is, let's see, we're in my examples. I could, where is, oh goodness, where is my, I thought I had a, yeah, I think it's here. Okay, how about I do 5? Let's save that. See how that is. It's a little more complicated, but let's see, the log likelihood is improving. So these are kind of the generative locations. We had 1 at -11, and we have 1 at -11. We had 1 at -6 or so, and it looks like we don't quite have 1 at -6 yet, but we do have 1. So you can kind of see, you know, it. Oh, here we go. Now this one that was, it's kind of the -4 is racing toward perhaps -6. Maybe it'll converge there. Do people kind of follow this? Is this cool to watch, or is this kind of like, okay, I'm getting some nods of the head here. Yep, okay, now that one here, this one here has stabled at about -6.24. That's like very close to the original. So the locations are converging quite nicely. Okay, and it's done. And it looks like it basically was able to recover the original distribution. Took a little longer, but then, you know, you might say, well, this is only 5. Okay, you get what I'm saying. This is more difficult the more components you have, and you know, when you can kind of qualitatively see this in the example here. Okay, maybe here this kind of looks like it maybe it could just be 1 Gaussian. Why are we doing a mixture of 2? If we didn't know where this data came from, maybe we just guessed it came from 1 Gaussian. But that's out of ways of evaluating how many, in the real world, we don't know a priori how many mixtures things came from, or maybe in some instances we would, but generally that's not the case. You can use things like cross-validation to use like a systematic holdout method to evaluate different values for the number of mixtures that you have. Just kind of do like a k-fold cross-validation and kind of see like which numbers work best. But I forget what I was going to say next. But so this is one. Oh, and then I also implemented Lloyd's algorithm where just for the sake of showing k-means, this is for like a very small data set, I think. Let's see if I can kind of make this a little bigger. Let's say I have 5, I have 10,000 data points. So actually, this is kind of not a great example. What I'm doing here, I've created a few. I'm creating a data set where I'm just creating a Gaussian mixture, basically sampling from a Gaussian mixture where everything has like it's centered at it looks like 0, 1, 2, 3, and 4, and then with a standard deviation of 1. just like each of them. And then let's see. So I should just kind of get back very simple. Let's see. Okay, so here we go. Means. I've said like, okay, you know what? I think there are means at 0.27, 1.7, 2.9, 4.2, and 5.7. So I'm not going to go into Lloyd's algorithm too much, but this is like a, I'm sorry I don't have like a better example for this, but it's like it's much faster to compute updates. As you see, like the iterations here took probably 100 milliseconds an iteration or so, and the data set was just as big or even bigger than for the Gaussian mixture. So yeah, and I think maybe a last thing that I'll say is I also oh, maybe that's kind of like the last thing. Yeah, I'll just kind of go over briefly one other implementation that I did, which was instead of using the expectation maximization algorithm, where we kind of very explicitly do these probabilistic assignments and then updates of parameters based on those probabilistic assignments, and then kind of go in that loop. One thing you might be thinking is like, okay, with a Gaussian mixture, for a given training sample, I can compute a probability, a PDF. There was that PDF function in the Gaussian mixture. So what if I just did gradient descent? Did like a likelihood gradient descent, where maybe I just kind of set all those kind of parameters for the Gaussian mixture, which, to recap, were the weights, their locations, and their scales, as just kind of parameters to be optimized, and just find, just kind of like do a gradient descent walk in, or gradient ascent to find the peak probability of my data given those parameters. We can do that too. And so to do that, I used a version of I didn't use TensorFlow, but like another library that lets you do kind of NumPy-like operations and differentiate them, called JAX, JAX. I highly, if you ever kind of want to do like have a bunch of NumPy code and you want to compute derivatives of it and not have to implement it yourself, you can just like swap out NumPy with this thing. It message me on Slack if you're ever interested in doing this. But that works too, but it's much slower than expectation maximization. Like it takes, this is the same example, if you remember, that took 36 iterations with EM, where the original is like 0.44 and 0.55. This is the same example running, but instead of doing that EM kind of iterative update, we're just doing updating the parameters based on the gradient of the log likelihood of the mixture based on the data. And it takes a lot slower. You could say, well, what if we try speeding up the learning rate here? Maybe it's just like learning too slow. It also, if you like learn too fast, you can kind of like you have unstable learning, which I guess is kind of always a problem with a lot of gradient descent things, but it's just like not nearly as well behaved. And it takes the previous algorithm, EM took 36 iterations, and this is taking roughly 1,000. It's just about done, I think. But down here, I show like how much it's improving. Okay, now the improvement is slowing down, so it's probably converging.
There's just some questions in the chat, Will.
Oh yeah, thanks. Sorry, I didn't have them side by side. Oh yeah, what is the advantage? It was just pedagogical. I was just kind of curious how it would look, and also doing it seemed like a natural thing to try out, because a lot of, like a lot of like statistical learning is we're kind of doing iterative optimization in a differentiable loss function. And a very natural loss function to consider here is, well, I'm learning a probability distribution. So why don't I just kind of see if I can improve the log likelihood of it? And the answer is that it just takes like a longer time. And this is also discussed a little bit in Bishop's text. If you look up Gaussian mixture modeling and like different ways for solving it. So was there anything? Oh yeah, I am in the ODEV Slack channel. I am. Yeah, I should be like, you find me, I think I'm visible as that, but maybe it's actually just William. Let's see. Oh yeah, Ron. I'm sorry, Ron, that I'm only seeing your message now. Purpose of the unsupervised. Yeah. Oh yeah. Okay. And so I'm reading a message in the chat here. How would I choose 2 versus 5? Like, how would I select the number of Gaussians? I think I mentioned you could use cross-validation. There are other ways too that are fancier. Who here is familiar with Zubin Garamani? I think he's like one of the people who led Google, not Google, right? DeepMind. And now he's a lead scientist at Google Brain. He just joined a few months ago. About 20 years ago, he did a postdoc with Michael Jordan at Berkeley. Michael Jordan is like one of the top machine learning people. He's called like the Michael Jordan of machine learning, but like his name actually is Michael Jordan, so it's kind of funny. Zubin Garamani developed this type of modeling called an infinite Gaussian mixture model, where it's a Bayesian approach where you start out with like 2 components, and then you can kind of like iteratively split and recombine components and have an arbitrary number of components and kind of sample and kind of explore in that space, and kind of develop a holistic explored space where you kind of are able to evaluate what is the probability that maybe my data comes from 2 clusters or 3 clusters or 5 clusters, all at the same time, kind of treating that number of clusters as also like an unknown variable that you can vary probabilistically. So that's like another kind of more fancy method, and I don't know how that works, so please don't ask me. But it's called infinite mixture modeling. Yeah, infinite. That's my keyboard. Infinite. I think it was. I think if we go on Nerd Alert, we're going to go on Google Scholar. Gaussian mixture. I think. Carl Rasmussen. Yep, at Oxford or Cambridge, I forget, but maybe it was actually Carl Rasmussen, but I thought Zubin Garamani did. Oh, maybe I might be thinking of the infinite hidden Markov model. Yeah, this was okay. So sorry, I misspoke. It was Carl Rasmussen, who is like one of the top cited machine learning people as well. So yeah, this was like 20 years ago, where people were, this was before deep learning was a big thing, and the number one method for doing things like speech to text and stuff like that, and doing speech processing, were these things called hidden Markov models, which are another type of latent variable model, very similar to Gaussian mixtures actually. So if you ever kind of study things like hidden Markov models, basically what they are instead of a bit Gaussian mixture model, what we've done now is kind of like a static thing where we say, you know, our data comes from some mixture, and if we were to sample a new value from that mixture, you know, we would first randomly decide which mixture we're going to sample it from, and then sample from that Gaussian. The hidden Markov model is useful in kind of like temporal data or longitudinal data or seasonal data, where maybe there are certain kind of background processes happening that are kind of like maybe at one point in time, your data is coming from one generative process, and then maybe it switches to coming from another generative process. And a way of kind of modeling, so for example, it would be like if you're speaking, an example of hidden Markov models is what syllable you're speaking. So you can kind of like decompose speech into, well, maybe like over the next 30 milliseconds or 150 milliseconds, my voice is speaking syllable 1, or maybe then I transition to syllable 56 and then syllable whatever. It's a way of kind of doing a dimensionality reduction of this kind of sequential data. Maybe for some period of time, I'm going to be sampling from one sequence, and I'm going to transition to sampling from another thing. So like these hidden Markov models were really effective in doing speech processing. I'm going on a little bit of a tangent here, but it all ties back to the same principle behind Gaussian mixtures, because we are positing the existence of an unobserved kind of collection of sources of data, and each of which maybe has some different mechanism of producing results. So for a Gaussian mixture, we have a collection of Gaussians, and each one of those Gaussians has a different mean and standard deviation. And this method, these algorithms here with like expectation maximization, give us a nice way of learning what we think those are. So yeah, this was like the infinite Gaussian mixture model, which I'm surprised it's only been cited 1,500 times. But it seems like infinite hidden Markov has been cited even more. And these were also in NeurIPS like 20 years ago. So that's kind of cool. Are there any, I'm ignoring the chat again. Shucks, where did the chat go? I missed the chat. Oh, here we go. Yeah, sorry I missed you, John. I will close out by saying, if you want to see this code, I have a repo where I kind of put all this together. I'll just paste this in the chat. It uses, I was kind of experimenting with a tool chain called Poetry, which is a way to, the way that I structured this project is Poetry is a Python tool for creating libraries and maintaining libraries, where you can like, it's similar to like YAML or NPM in the JavaScript world, where you can do like dependency management. It'll create virtual environments for you. It will publish updates of your library to PyPy for you. Does like a lot of things, but it also is kind of, it's like yet another tool, right? So I don't really use it as much anymore. So anyway, that's my talk. If there are any questions.
Yeah, no, we can also add your GitHub as a comment in the Meetup page.
That makes sense.
Yeah, for the event. And your contact info as well, if, yeah.
Yeah, sure.
The link is in the chat. Do you, I mean, if you, oh, okay. Yeah, so are there any last questions? Okay.
Let's see. Ricardo asked, oh, what's the name? Did someone ask what's the name of the method? Oh no, I think just my chat screen was showing something weird.
Okay, so if there's nothing else, yeah, I guess we're done for today. Sorry for the hiccup in getting into Zoom. We'll fix that for next session. We'll post a recording and I guess the stuff mentioned in this talk, the book, the GitHub, Will's contact information as a comment in the Meetup page along with that. You're also all free to stick around for like 30 minutes if you want. I should stop the recording.